Okay, so what I was trying to say is that this is the linearization, right? And now if I look at this linearization with multiple variables, then what happens is that if I just want to look at the behavior where the point goes, that's going to be the slope part, which is going to be this part right here. So I rewrote this part in matrix form, and then here I took the derivative of L1, L2, which is the slope. So I can say that this is a derivative and that this is x minus x naught. And to do this, I would have to say, actually, that this is x prime and this is y prime. And now we can say that. And so this is x prime, y prime. And then I notice that this is equal to this matrix system right here. And now if I let h equal x minus x naught, and I take the derivative remembering that this is just a vector of constants, then I get that h prime is x prime. So I can write that here, remembering that this is the Jacobian evaluated at my critical point. And then if I look at do this guessing method and I guess this as a solution and I carry it through, I end up with this, which is the eigenvalue problem. So that's why we want to find the eigenvalues. So we evaluate it at the critical points, and then we find the eigenvalues. Find the eigenvalues. Values. So that's going to be, the determinant must be equal to 0. So 2 times 0 minus 1/2 times 4 has to be equal to 0. So, well, not exactly that. We have to first subtract lambda to the diagonals, and that comes from the eigenvalue problem. And then we do the determinant is equal to 0. So 2 minus lambda, and I can factor out a negative sign, so minus lambda minus 2, and minus lambda minus, and this is just a negative 1, and this is minus 4 times 1/2. All of that has to be equal to 0. So what we get is that these two negatives cancel out, and here we get lambda minus 2 times lambda. So this is going to be lambda squared minus 2 lambda minus 2 is equal to 0. And so let's see. One numbers added together are equal to -2, and multiplied together are equal to -2. I don't know. So let's just complete the square. So if I add a 2 here, I'm going to have to add it here. And I actually want to add a 4 because I'm taking half of this and squaring it. So I want to add a 4 here. And so I get lambda minus 2 squared equals 6. So now I take the square root and I get lambda minus 2 is equal to plus or minus the square root of 6. So lambda is equal to 2 plus or minus the square root of 6. Now the square root of 6 is less than the square root of, let's say 9, which is 3, but it's greater than the square root of 2. So I know that we have lambda 1 that is less than 0 and lambda 2 that is greater than 0. And now because of that, I know that this is a saddle. And another way to do it would be to look at the determinant of this. Well, not of this, of the matrix. So a second way would be just look at find the determinant of the matrix 2, so the Jacobian, 2, 1/2, 4, and 0. And if you do that, that's going to be, I'm going to indicate the determinant with the capital Greek letter delta is going to be 0 minus 1/2 times 4, which is 2. And when the determinant is 0, is less than 0, sorry, it's a saddle. And this comes from a graph that was done using the trace and the determinant that I'm going to show you right here, which I think is pretty cool. So if you look at, where is it? This graph over here, it tells you, hey, well, in our case, we had a determinant. This is the determinant axis, less than 0. In anything that's less than 0, it is a saddle. So now if we go back and actually bubble the answer right here is going to be saddle. I hope this was useful and it didn't confuse you. It did help me think a little bit deeper about what we're doing. And I'll see you next time.